In this video, we will explore the naming of alcohols and their physical properties. The first thing we're going to do, which is very similar to what we have been doing thus far, is identify the longest continuous carbon chain. And we have to make sure that that carbon chain contains the alcohol. And then we're going to use a prefix to indicate the number of carbons, just like we've been doing before. And we will end with all to indicate that it's an alcohol. And before we get further into it, I just want to make sure that we understand what an alcohol is. That'll be any hydrocarbon that has an OH group on it. So this R group could be virtually anything. In the example on the left, we see that it's a 5-carbon long chain. It could be any number of carbons. As long as it has an OH group, it's an alcohol. So looking at that example up top, I'm going to find the longest continuous carbon chain. I see that it's 5 carbons long. So the parent name, we're going to use the prefix pent to indicate that there are 5 carbons in it. And if this was just a regular alkane, we would call it pentane. But because it has an OH group on it, it's an alcohol, so we're going to change that E ending to all. And that parent name will become pentanol. The next thing we're going to do is number the carbon chain to give the carbon directly attached to the OH group the lowest possible number. When we were naming alkanes, we were prioritizing the substituents and giving them the lowest numbers we can. And that was because alkyl groups and halides all have the same priority. Here we are prioritizing the OH group. Even if there are substituents in the chain, that OH group needs to have the lowest possible number, even if it is at the expense of substituents. Which means in this scenario, I'm going to number left to right, because in that case, the OH group gets number 2 versus number 4. If the parent chain is 3 carbons or longer, then we will indicate the number of the carbon that is directly attached to the OH group. Which means, looking at our previous example, we need to indicate that that OH group is on carbon 2. So we said that our parent name was pentanol to indicate the fact that there are 5 carbons in there. But we're actually going to call it 2-pentanol to indicate that that OH group is centered on carbon 2. Because it could really be anywhere in the chain. We could have something like this, for instance, in which case it's on carbon 3. And we have no idea where that OH group rests unless we indicate that numerically. Now, the reason this is not important if you have a carbon that's if you have a carbon chain that's less than 3 carbons long, is because regardless of which way it's drawn, this carbon is going to be number 1. And if we had drawn it in the other direction, well, then we would number in the other direction and we would get the same numbering system. So if it's less than 3 carbons, it really doesn't matter. It'll always be on carbon 1, so we don't need to indicate then. The last scenario we will explore is if it is a cyclic alcohol. then the carbon that is directly attached to the OH group is carbon 1. And then we're going to have the same rules as cycloalkanes. We can either number clockwise or counterclockwise to give the rest of the substituents the lowest possible number. The only difference will be that we will end with all to indicate that it's an alcohol. So other than that, same rules as cycloalkanes, but end with all to indicate that it's an alcohol. Let's try a couple of examples. Okay, one thing I want to make sure that we're very careful with is these two are very commonly mixed up and they are very, very different things. On the left, I see that we have a cyclohexane attached to an OH group, so that would be cyclohexanol. On the right, we actually have a benzene attached to an OH, and that was one of the special aromatic cases that we called phenol or phenol. These are very, very different from each other. They have different shapes, they behave differently, so be very, very careful not to mix them up. If you see these double bonds throughout the ring, that's a phenol. Notice that cyclohexanol is just an alkane with an OH group attached to it. So these are all single bonds. They have different numbers of hydrogens. They behave completely differently. So just don't mix those up. Let's try an example. Okay. The first thing I'm going to do is look for the longest continuous carbon chain, and it looks like that will be directly across. And then I'll figure out the parent name. So whenever I'm doing these types of problems, I always ask myself, well, what would the regular alkane be called? And I see that this has 7 carbons. And if it was an alkane, we would call it heptane to indicate that there are 7 carbons. Well, I'm going to take that E ending and change it to all to indicate that it's an alcohol because it has this OH group on it, which means the parent name will become heptanol. And then I do need to indicate numerically where that OH group appears, and I'm going to number right to left to give the OH group the lowest possible number. And since the OH group is on carbon 2, I'm going to call this 2-heptanol. The next thing I will do, just like with all of the other naming, is look for the substituents and make sure I list those two. This substituent has 2 carbons, which means it's an ethyl group, and it's attached to carbon 4, so we would call that 4-ethyl. And then just like standard alkanes, I'm going to list the substituent name first and then the parent name, which means this becomes 4-ethyl 2-heptanol. Let's try a cyclic example. I'm going to use my little templates here. Okay. All right, the first thing I'm going to do is figure out the parent name. And this ring contains 7 carbons and it's cyclic. If it was a regular alkane, we would call it cycloheptane. Cyclo to indicate that it's cyclic, hept to indicate that it has 7 carbons in the ring. But because it's an alcohol, we'll change that E ending to all, and that becomes cycloheptanol. Now, when we're numbering the ring, any carbon can be carbon 1, but because the OH group takes the highest priority, the carbon directly attached to OH will be carbon 1. And then we can number either clockwise or counterclockwise. If I number clockwise, then the next substituent is on carbon 3. If I number counterclockwise, then the next substituent is on carbon 4. And I want the version that gives the substituents the lowest possible number, so I'm going to number clockwise. And then as usual, I'm going to list where the substituents are and put them in alphabetical order. I see that there's a 3-bromo right here, and then there is a 5-methyl on this side. I need to list them in alphabetical order, and B appears first, which means this becomes 3-bromo, 5-methyl, cyclohexane. And here I don't have to indicate where the OH group appears because it's understood that it's going to be on carbon 1. In cyclic cases, we prioritize the numbering of the OH group, so it's a little redundant to put in that number. Let's try one more example. Okay. The parent name here, to figure out the parent, I'm going to find the longest continuous carbon chain as usual. I see that it is 7 carbons long, which means the parent will be heptanol. And then I need to figure out whether I'm going to number left to right or right to left. I'll explore each option. If we go left to right, then the OH group appears on carbon 4. If we go right to left, the OH group appears on carbon 4, which means as far as the alcohol is concerned, it really doesn't matter. So then we're going to have to use the substituents to break the tie. I see that in the top version, when I went left to right, the first substituent appears on carbon 2. If I use the bottom version, then the first 2 substituents appear on carbon 3. And we want to give the substituents the lowest numbers we can, so I'm going to use the left to right version, not the right to left. And then I'll list the substituents. I see that here we have a bromo on carbon 2, so I will call that 2-bromo. And then on carbon 5, we have 2 methyl groups. Keep in mind that when we have 2 of the same substituent, we're going to use the prefix di. This will become dimethyl. And then we do need to indicate the carbon number for each of them. They're both attached to carbon 5, so I'm going to call this 5,5-dimethyl. And recall that it's important to list this number twice because that tells us that both of them are attached to carbon 5. Otherwise, we won't know. It's possible for one of them to be on carbon 5, maybe the other one was on carbon 6. So we do have to indicate that they're both attached to the same carbon number. Now we're going to alphabetize. And when we use the prefix di, tri, tetra, etc., those are not considered when alphabetizing. So here we're going to alphabetize by M. For B, it's straightforward. We will alphabetize by B, which means 2-bromo is listed first, then 5,5-dimethyl. And then I do need to indicate the location of the OH group, which is on carbon 4, and I will call that 4-heptanol. And that is the full name of this particular alcohol. We can also classify alcohols similarly to what we did in previous videos where we classified carbons. And really what we're going to do is see that carbon that is directly attached to the OH group, we will see how many carbons that particular carbon is attached to. If it's directly attached to one carbon, then we will call that a primary alcohol. And this is all based on the classification of that carbon that is directly attached to the OH group. It's attached to one carbon, primary alcohol. If instead it was attached to 2 carbons, then we would call it a secondary alcohol. Ooh, one of these should be an OH. There we go. And finally, if that carbon is attached to 3 carbons, then we call it a tertiary alcohol. Note that we can't have a quaternary alcohol because one of these attachments has to be an OH group or it wouldn't be an alcohol. And carbon can't make more than 4 bonds, so tertiary alcohols is the largest that they could possibly get. One of the really important physical properties of alcohols that we will explore is their solubility in water. And if you recall, solubility is really dependent on how polar or nonpolar a particular compound is. So if you look at the structure of water, it has this bent molecular shape, and the oxygen has a partial negative charge because it's very electronegative and it's pulling electron density toward itself. The hydrogens have a partial positive charge because they are less electronegative than oxygen, and some of their electron density is being pulled toward oxygen. So water is very, very polar. The dipole is going in this direction, which you can represent either with a little dipole arrows or with the partial positive, partial negative charges. And the strongest intermolecular force in water is hydrogen bonding, which means that if another water molecule is present, it is going to orient the partial negative end of the oxygen toward the partial positive end of the hydrogen because these opposite charges attract, and that is the hydrogen bonding interaction. If you recall the like dissolves like rule, what this really means is that polar compounds will dissolve other polar compounds, and nonpolar compounds will dissolve nonpolar compounds. So let's look at the structure of alcohols and think about how their structure affects their polarity. So it'll look similar to water in that it has this bent shape, it has an OH, but instead of one of these hydrogens, we will have an R group. And that R group is a hydrocarbon chain that can have varying length. So we do have a partial negative charge right here. We have a partial positive charge on that hydrogen, which means this end of the alcohol will engage in hydrogen bonding. But if we look at that R chain, that could have varying lengths. It could be a couple of carbons long. It could be many, many carbons long. Now, if we were to zoom in, these are currently in the line angle format, but we could expand these out to see exactly how these atoms connect. I'll expand the shorter one down here. I see there's one carbon here and another carbon right there. Maybe I should draw them in the same conformation. Okay. This carbon needs to have 2 hydrogens to complete its octet. That end carbon 2 needs to have 3 hydrogens to complete its octet. So notice that on that R group, or the hydrocarbon chain, we have a carbon-carbon bond. That's definitely nonpolar. We have 2 carbons that are attached to each other. Their electronegativity difference will be 0 because it's the same thing bonded to itself. Definitely nonpolar bond. If you recall, CH bonds are also nonpolar. And if you're not sure about that, you can go ahead and calculate the electronegativity differences between carbon and hydrogen. Which means that on this end of the molecule, these are all nonpolar bonds. And nonpolar bonds, the only intermolecular force they have is dispersion. Which means that one end of the molecule that engages in hydrogen bonding, that OH part, will be soluble in water, but the nonpolar end, not so much. That's not going to mix very well with a polar solvent. So the solubility of alcohols will really depend on how long that R group is. If we have a really small alcohol, like the one we just drew, that is ethanol, that's drinking alcohol, and that's definitely very, very soluble in water because we have a hydrogen bonding interaction right here. And sure, we have some nonpolar dispersion interactions here, but this chain is fairly small, which means that that hydrogen bonding interaction is pretty significant, and it will be able to override those dispersion forces in that small R group. Now, if that chain got really, really long, this would not be so soluble in water. Sure, we have a little bit of hydrogen bonding here, but then we have this really, really long nonpolar chain that is not going to dissolve in water. And effectively what this means is the more OH groups and the fewer carbons that an alcohol has, the more soluble it is in water. So the general guideline is that between 1 to 3 carbons, they tend to be very soluble or miscible. If it has about 4 carbons, it's slightly soluble. And 5 carbons or more, alcohols tend to become insoluble in water because there are just so many dispersion interactions that they kind of override the hydrogen bonding. And note that you can actually make a chain more soluble by just adding more OHs. So if I have one OH group, that wouldn't be particularly soluble in water. But if I take 5 carbons and I attach a few more OH groups to it, that starts to increase its solubility because now I have more and more hydrogen bonding interactions that can compensate for the nonpolar interaction.